All right, so we're very glad to have Michael Ching talking today, who's up early in the morning. So thanks very much for offering to give a talk, Michael. And you can start when you're ready.
Well, thank you very much for the invitation, and thank you all for coming. It's certainly a pleasure to talk about this, and you know, it's a pleasure to be virtually in the Czech Republic. Yes, good morning from America. I've had some coffee, so hopefully I'll manage to stay awake for the whole talk. We'll see. All right, so this is a project that I've been doing for a few years, and it's hopefully I can advance. Yeah, so it's a project joint with Christine Bauer and Matthew Burke, and we posted the preprint a couple months ago. So this talk's going to be based on mainly on that first preprint at the top there, tangent infinity categories and Goodwille calculus. And if there's time, I might mention a sort of follow-up shorter article that's the second one. And this whole project was really inspired by another paper, so I wanted to give credit to that, and that's Christine Bauer, Brenda Johnson, Christina Osborne, Emily Reel, and Amelia Tebby, and you know, the kind of basic question that we're trying to answer arose from that paper, and so that's sort of the starting point for the kind of connection that we did in our project. So let me try to explain sort of the one version of the motivation, and you could think of it as trying to understand and connect two meanings of the phrase tangent category. And if you go on the NLab and read about tangent category, then well, there are sort of two meanings described there. They're given slightly different names. So the meaning of tangent category on the NLab is the following. It's the category of abelian group objects in the slice categories over C, which are also called Beck modules, I think. A lot of this talk will be more about the kind of infinity categorical version of some of these ideas, and so there is a homotopical or infinity categorical version of the Beck modules, which you could think of as parametrized spectra in the sense of stable homotopy theory. So those are sort of analogs, and both of them you could call the tangent category or the tangent infinity category on another category C. The second meaning, which on the NLab is given the name tangent bundle category, is actually the one I'm going to start off talking about, and maybe the one that's perhaps familiar to some of you. And this, if you have a tangent bundle category in the terminology of the NLab, then that gives you for each object of the category something that plays the role of the tangent bundle. So another object T of C, together with a lot of structure maps that sort of play the role of the usual structure maps you get in the category of smooth manifolds and smooth maps. So that category of manifolds is sort of the prototypical example of a tangent bundle category. So the real goal of this talk, or the first goal, you could express as trying to connect these two meanings by showing that number one is actually an example of number two. And that's sort of where we started with this project, is trying to show that that if you have an infinity category C, then this homotopical infinity category of parametrized spectra actually does play the role of a tangent bundle, and you have all of the rest of this structure that's analogous to what you have for the category of smooth manifolds and smooth maps. So in the literature, both of these meanings are given the name tangent category in general, and so just one warning, we will, in our paper and in this talk, I'm going to use tangent category for meaning number two, which fits with the literature on these objects, as I'll explain in a second. And I actually think that it makes more sense to call number one the tangent bundle category, because it is playing the role of the tangent bundle, and I'll get to that a little later. All right, so let's start with number two here, and this theory of tangent categories in that sense. So this notion was first developed by Rositzky in 1984, and then developed much more recently by Cockett and Crutwell. And so as I understand it, and obviously Yoshi can give more correction if I'm misrepresenting the motivation here. One of the ideas is just to try to axiomatize some of the categorical properties of the tangent bundle functor. So the tangent bundle gives you a functor on the category of smooth manifolds and smooth maps, and you want to try to axiomatize some of the properties of that functor and apply them to other categories. So what does that look like? So here is sort of the beginnings of a definition of this notion of tangent category or tangent structure on a category X. So we should start with an endofunctor that plays the role of the tangent bundle functor. And then we want to describe the structure, the other remaining structure maps that sort of tell you that this, it does play some kind of tangent bundle role. And just from your knowledge of ordinary tangent bundles on manifolds, there are quite a lot of the structure you can kind of naturally write down. So the tangent bundle has a projection. So we would expect to have a natural transformation that gives you the projection maps from the tangent bundle down to the manifold. The tangent bundle is a vector bundle. So in particular, it has a zero section. And it has an addition, giving you the addition in the vector bundle. So that's a natural map from Tm crossover M with Tm to Tm that adds two tangent vectors. And you can keep going, and the more you think about the tangent bundle on manifold, you can try to work out what other structure or what other properties to include. And in this definition of tangent structure, there's sort of two more pieces which both concern the double tangent bundle. So one way to think of which properties of the tangent bundle functor are we trying to axiomatize? It's sort of things giving you properties of T, but also of the double tangent bundle or T of Tm. So there's a symmetry that flips the two tangent directions. If you think about the tangent bundle to the tangent bundle on the manifold, then there's two directions, and they're actually symmetric. And just a little bit of thought about ordinary tangent vectors, you can figure out what does that symmetry actually look like. And then maybe the sort of most not mysterious, but the one you might not have thought of as naturally is called by Cockett and Crutwell the vertical lift. So that's a natural transformation from T to T squared, and it sort of takes it's sort of a diagonal on each tangent space. So it takes a tangent vector and gives it in the double tangent bundle, it maps the tangent vector to a kind of diagonal. All right, so here is the data of a tangent structure on a category X. And then, of course, there are conditions. And so the first condition is that lots of diagrams have to commute. And I'm not going to try to write down or say what those diagrams are. You can probably imagine many of them. For example, they tell you that the tangent bundle is to some extent a vector bundle. So for example, addition is commutative, addition is associative in the tangent bundle. So There are lots of diagrams that express, again, properties that you know of from the ordinary tangent bundle on a manifold. And then the second, I'm going to highlight one particular axiom. So there's lots of diagrams that have to commute, but then there's an extra condition, which is that a certain square is a pullback. At least that's one way to phrase it. You can also express this as an equalizer condition, but I like to view it as a pullback. And so it says that for each object M, there is a pullback square that looks like this. Essentially, if you pull back the double tangent bundle over the zero section, then what you get splits as this sort of fiber product of two copies of the tangent bundle. So I like to highlight this one because for a couple of reasons. Partly because it's really the only axiom that isn't just saying that some diagrams commute. There's in a sense more substance to it. It sort of feels like, it's interesting to think through what it actually means. That in this category of smooth manifolds, as I've written below, you can think of it as a sort of splitting of the tangent bundle on a tangent space. And that's something that's familiar. A tangent space is just a Euclidean space, and it has a trivial tangent bundle. And you can think of this vertical lift axiom as expressing those splittings in a manner that is sort of smooth over the whole manifold. And Cockett and Crotwell in their sort of analysis, they really try to emphasize that it's this axiom that gives you a lot of the theory, a lot of the kind of subsequent theory that you develop for tangent categories ultimately relies on this axiom. Without this axiom, in a sense, you've sort of got some maybe more superficial information about a tangent bundle functor and commutative diagrams, but this actually says something a bit stronger, which has important consequences. Okay, so that is the tangent, the definition of tangent category, or the first definition. Let me, I guess, mention some examples. And so, as I've said, the category of manifolds with it, the ordinary tangent bundle is the sort of motivating example. But why was this notion developed? To make connections with other areas in which you have a notion of differentiation or a notion of tangent vector. These next two are things I don't know much about: synthetic differential geometry and the differential lambda calculus of Earhart and Régnier. But they both fit into this framework, and part of what Cockett and Crotwell did, at least, was to try to show how some of these different examples fit together into the same framework. There are also some more familiar examples, at least more familiar to me, and in particular, just the category of commutative rings has a tangent structure. It actually has two tangent structures. So one given by this sort of dual numbers construction. If you have a ring, then you can form the polynomial ring and quotient by the quadratic term x squared. And then in a dual to that, there's a tangent structure on the opposite category of commutative rings, which is given by basically the symmetric algebra on the module of Kähler differentials. So there's a couple of sort of interesting and those two structures, they're one on rings and one on the opposite category. They are dual in a particular sense. In fact, those two tangent bundle functors are adjoint to each other. And if I have time, if I get to talking about the sort of follow-up paper to do with infinity toposes, then I'll come back to that relationship. And the last example there, the category of schemes is an extension of the opposite of the category of commutative rings, and the tangent structure on opposite of commutative rings extends to a tangent structure on all schemes, which sort of recovers the Zariski tangent spaces in the usual sense of algebraic geometry. Okay, so those are a few examples. What I want to turn to now is to talk about how in our project we extended tangent structures to infinity categories, and that was sort of the first part of our project. We have these definitions of tangent category, but the context that we wanted to work in, which was the infinity category, tangent structures or tangent bundles on infinity categories, we needed a generalization of what I've already told you. And maybe I'll just say a few words about that process. The definition that I've given you, I'll just go back to sort of, here is the definition that I've shown you. We have an endofunctor, we have 5 natural transformations, and we have lots of diagrams that have to commute. This is not a very convenient definition for generalizing to infinity categories. And the main sort of reason for that is that whenever you have commutative diagrams in an infinity category, you really expect to have higher coherences. So the diagrams now just commute up to homotopy, and you expect to have higher homotopies between those homotopies, and figuring out the combinatorics of all of those different sort of homotopies and coherences is typically it's complicated, and it wasn't clear to us when we started this project how to capture the right sort of higher dimensional information. So fortunately, there's a different description of the definition of tangent category due to Poon-Leung, and this one turns out to be much more convenient for extending to infinity categories. So let me tell you about this this other definition which uses Weil algebras. All right, so here is the sort of fundamental definition for Leung's kind of characterization of tangent category, and that is a monoidal category of Weil algebras. Weil algebras in general is sort of a much more it's a much more general term. It covers a much wider collection of rings or semi-rings than the ones I'm describing here. But this is the category that for Leung's definition that turned out to be important. So let's define a monoidal category. The objects are these augmented commutative semi-rings. So they are just start with the natural numbers, take a polynomial semi-ring, I guess, a polynomial algebra over the natural numbers. So notice that I'm sort of ruling out the need for additive inverses here. So we're taking these semi-rings rather than rings. Anyhow, so from one of these polynomial algebras, we quotient by some collection of quadratic monomials, so we're going to quotient by xi, xj, where there's some equivalence relation on 1 through n that tells us which quadratic relations to quotient by. And then the morphisms in this category are just the ring or semi-ring homomorphisms that commute with the augmentation. And there's a monoidal structure, which is given by the tensor product, which just concatenates the list of generators. So here are some just examples to be a little more concrete about some of the basic objects in this category. So if you have just a single generator, then there's only one way to take the equivalence relation, which is to quotient by x squared. And so we get an object which we could call W, which is just nx mod x squared. If we move up to two generators, then there are now two different equivalence relations on a set of two objects. So we can either quotient by all the quadratic relations or just x squared and y squared. And so that gives us two Weil algebras. And it turns out that one of them, the first one there, is just the product of two copies of W, and the second one is the tensor product of two copies of W. And the tensor product actually is also the coproduct here, so that's the coproduct of two copies of W. And you can extend both of those constructions. So I could take some larger product of copies of W, which, if you work out the details, amounts to just quotienting by all the quadratic relations. So that's the sort of trivial, or forget the right word, indiscrete equivalence relation corresponding to the full partition. And then you can take the coproduct or tensor product of copies of those products. And it turns out when you do that, you get up to isomorphism, you get every object in this category. So every object is of that form I've written at the bottom here. It's a tensor product of these products of W. Okay, so that's the category of Weil algebras. So Leung noticed that the structure of this category really captures all of the structure of a tangent category. So here is Leung's theorem then. A tangent structure on a category X can be recovered from, or can be identified with, a monoidal functor from this category of Weil algebras to the category of endofunctors on X. And there is a condition, and that's that certain pullbacks in the category Weil are preserved. In particular, there is a condition there that implies the vertical lift axiom. That axiom I mentioned earlier, that is, says that a certain diagram must be a pullback. So that's captured by one of these pullbacks that has to be preserved. Let me unpack this a little bit for you. And connect it back with the previous definition. We have each Weil algebra. This monoidal functor gives us an endofunctor, Ta. So Tn, where n is just the trivial, the unit for the monoidal structure, that has to be the identity functor. And then corresponding to that Weil algebra W with one generator, that gives us the T that is the tangent bundle functor, that plays the role of the tangent bundle functor in the tangent structure. And then these other two Weil algebras with two generators correspond to the double tangent bundle and this fiber product of T with itself over the identity. And that's that T cross over I with T, that plays the role of the, or that gives you that sort of fiber product of giving you two copies of two tangent vectors over a point. And then I've put, I've written out, I won't read through this, but I've written out here how you get each of the natural transformations in the original definition, just by applying the functor t, I guess that should be t with a dot, to various different morphisms in the category V. So you can recover all of the structure maps that I mentioned earlier from this monoidal functor on the category of V algebras. I think I was going to say one more thing. So okay, maybe before I move on to the infinity category version, then maybe I'll just check to see if anyone has any questions so far. Just to give myself a break so I can have a sip of coffee as well.
I guess that's the same as sort of, well, module over this monoidal category. But
yeah. So you could think of this as saying that X is a module over V, or an actagory is another term for these things. So it's a category with an action of the monoidal category V. All right. So this theorem, or this version of what a tangent structure on a category is much better suited for extending to infinity categories. In fact, it's so much better suited that we really can just copy it word for word, adding infinity in the appropriate place. So here is our definition of a tangent structure on an infinity category. It is, again, a monoidal functor from the monoidal category of V algebras to the infinity category of endofunctors. And we have the same requirement that those same pullback squares in V are preserved by this functor. The thing to note is that, of course, here when I write monoidal functor, this is now a monoidal functor between monoidal infinity categories. And so tied up in this definition is a theory of what is a monoidal infinity category, what is a monoidal functor between monoidal infinity categories, and also when I say the functor preserves the pullbacks, pullback in end of X means pullback in the infinity category sense. So of course everything in that definition is secretly, or not so secretly, an infinity category, or a notion of infinity categories. So the sort of first example that we give, actually, maybe it's not the first example, because the first example of tangent structure on an infinity category is just that every tangent structure on an ordinary category is also a tangent structure on the corresponding infinity category. So every category can be viewed as an infinity category, and so our definition includes all of the previous definitions of tangent categories, but it does have more things. And so this example I've written here is the infinity category of derived manifolds, which sort of originally due to Spivak, I think, and the particular version that we referred to is by Karkady and Stephens. This is an infinity category that extends the ordinary category of smooth manifolds, really to allow you to form pullbacks, fiber products along non-transverse maps. So in the category of manifolds, you can take pullbacks along two maps that are transverse, but in general, you don't have pullbacks. And so this derived manifolds is a way to sort of expand the category of manifolds to give you those extra pullbacks. And this is an infinity category. It can't be realized as an ordinary category. And so our first example of a tangent structure shows that the ordinary tangent bundle on manifolds extends to a tangent structure on these derived manifolds. Maybe I'll just point out that we can, we defined tangent infinity categories, but we also have defined tangent functors and tangent natural transformations. And in general, there is an infinity 2 category of tangent infinity categories. And then even more generally, the same definition that you see at the top here really extends to a notion of tangent object in any infinity 2 category C. Just briefly to explain that, an infinity 2 category is a world in which it's essentially enriched over infinity 1 categories or infinity categories. So for any object X, the category, the sort of endofunctors of X form an infinity 1 category. And so the definition that I've written at the top there makes sense whenever X is any object in an infinity 2 category. And so the sort of most general version of our definition at the top there is a notion of tangent object in any infinity 2 category, and an infinity 2 category of tangent objects in C. In particular, there's one particular case that we are interested in, which is confusingly when C is the infinity 2 category of infinity 2 categories, and that allows us to define a tangent structure on an infinity 2 category. So probably at this point you're a bit overwhelmed by the different roles that infinity categories and infinity 2 categories are playing, and I think for me that was one of the challenges of this project, was sort of disentangling the different levels at which these different kinds of categories act. We have a tangent structure on a category, we have a category of tangent structures. So that was all a sort of big headache in making sure that we understood what we were talking about. Anyhow, so that's our definition. And so now I'm going to move on. If there are no questions about this, I'm going to move on to sort of the second part of the talk, which is kind of going back to that NLab, the NLab definition. I said at the beginning, I wanted to show that definition 1 was an example of definition 2. So what I've shown you here on the screen is a version of that second NLab concept. And so now I want to go back and look at the first one and as I said, show that it's an example of this one. Let me just pause a second just to see if there are questions before we move on to that other topic. All right. So this is so now I'm going to describe another example, a specific example of a tangent infinity category, and even more confusingly, it is now this is going to be an infinity category of infinity categories, and so so now infinity categories are playing yet another role in this story, in that they are now the objects of my tangent structure. So they are now in this part of the talk, the infinity categories are now the analogs of the manifolds. So what is which collection of infinity categories are we going to define a tangent structure on? So here is a definition. We'll say that an infinity category is differentiable if it admits finite limits and sequential colimits, and those have to commute. And we can define an infinity category whose objects are these differentiable infinity categories, paying some attention to the size estimates, of course. And the functors are, the morphisms are the functors that preserve these sequential colimits. This definition comes from Jacob Lurie, and he defines differentiable infinity categories as a context in which you can do Goodwille calculus. Goodwille calculus is the sort of in a sense, the other half of this talk is about Goodwille calculus and how to connect it with the story of tangent categories. So I'm not going to sort of go into detail about what Goodwille calculus is, but it's in the background of this part of the talk. And that's why we call this tangent structure that I'm describing the Goodwille tangent structure, because it really captures Goodwille's calculus of functors and that theory. So to tell you about this tangent structure, I should first tell you what is the tangent bundle functor. What is the underlying functor T? And this is also a definition of Lurie. So in this generality, Lurie defines this notion of tangent bundle to an infinity category. And again, this is playing that role of number one, the number one definition on the NLab. This is the first of those definitions, but it's this homotopical version or an infinity categorical version, which you can view as parametrized spectra. So here is the definition. If we have an infinity category C, then we're going to define T of C, the tangent bundle, to be the infinity category of excisive functors from finite pointed spaces or finite pointed CW complexes to C. So the word excisive comes from Goodwille calculus, but all it means is that these are functors that take pushouts to pullbacks. So that gives us a definition of T of C, the tangent bundle on an infinity category C. And as I said, this sort of more intuitively can be thought of a collection of categories of parametrized spectra, or spectra over the different objects in C. To be maybe, I'll say out loud one precise thing: the fibers of this tangent bundle are the stabilizations of the slice infinity categories. So this is, as I said, the analog to the Beck modules or the abelian group objects in the slice the slice categories. I wanted, so that defines T of C. I also should tell you what T does on morphisms. So if F is a functor from C to D, then we can define T of F, a functor from T of C to T of D. And the basic idea is you want to just precompose, or I guess postcompose with F. Now, if you take an excisive functor and you just apply some other functor F to it, well, the result is likely not excisive anymore, unless F preserves pullbacks. So we take this P1, which is the excisive approximation, and that's also coming from Goodwille calculus. It's the Goodwille shows that any functor has an excisive approximation, sort of universal approximation by an excisive functor. And so this is our definition of T of f for a functor f. You should notice, or maybe if you sort of take a few minutes to write it down, it's not obvious that this is functorial, that this definition of T preserves composition of functors. And so there's a sort of a lemma that you need to prove to show that T of f composed with G really is T of f composed with T of G. And there's a fact from Goodwille calculus that tells you that is true. Okay, but that is our tangent bundle functor, and that's the kind of basis, or the starting point for the tangent structure. All right. Well, here is our theorem then. The theorem is that tangent bundle functor on the category of differentiable infinity categories extends to a full tangent structure in the sense that that we described before. I've written out in this box, I've written what is the projection. The projection sends an excisive functor and just evaluates it at the 1-point space. So that plays the role of the projection map, or the projection of the tangent bundle. And I've written out the zero section. The zero section takes an object and maps it to the constant functor with value that object. So that's the zero section, and so on. And I could write out the other kind of basic natural transformations in this definition. I've written out a kind of in more detail what the definition is. I think I don't want to spend too much time sort of working through this definition. Maybe the main thing I'll say is that if you have a Weil algebra, it's given by it has some number of generators. We define TA of C, so this is the functor corresponding to the Weil algebra A, as a sort of category of A excisive functors. So it's a sort of generalization of just the excisive functors. And notice that these are functors on functors of n variables, where n is the number of generators. So I don't have time to kind of spell that out in more detail, but that's basically how we define our tangent structure using Weil algebras. And sort of along similar lines, I won't say it, but I'll just I put this in the slides. We can define the tangent structure on morphisms of Weil algebras essentially by pulling back or by precomposing with a certain functors on spaces. So that's how we define this full tangent structure functor. So that was our main definition, and I said at the beginning that the goal was to connect the two notions of tangent category, and that is what we've done. Oh, I think I did have another slide which I was going to mention, this vertical lift axiom. I tried to tell you earlier on that the vertical lift axiom is somehow fundamental in the notion of a tangent category. And also for us in defining this tangent infinity category of infinity categories, somehow one of the key points was, is this vertical lift axiom true? What does that actually look like in our Goodwille tangent structure? And so sort of a central part of our proof was to show that yes, this corresponding diagram is a pullback of infinity categories. And this actually turned out to be a kind of interesting thing to work out, and to it uses more of the theory of Goodwille calculus to prove that that you have this sort of splitting result. It's a kind of splitting result for the tangent bundle of a tangent space, and Goodwille's theory sort of tells us exactly how to do that. Okay, so as I said, that kind of completes what I said was the main goal of the project, which was just to show that this sort of tangent bundle on an infinity category actually is an example of a tangent infinity category. So connecting the two notions from the NLab. But why do we? Why is this useful? Why do we care about the fact that this is an example? And one way to explain sort of why we care about this example is that it allows us to take ideas from the theory of tangent categories and look at them in our example and see what do they actually correspond to in the Goodwille tangent structure. So I've got a couple of slides just explaining some of these ideas where you take a sort of general notion from the theory of tangent categories and you work out what it looks like in your particular example. So here is one of the basic sort of examples of the theory of tangent categories, and that is a differential object. So Cockett and Crotwell define what is meant by a differential object in a tangent category, and the rough idea is that these are just the tangent spaces. These are the objects for which the tangent bundle splits is trivial and splits as just a product of two copies of the object you started with. So in the category of manifolds, these are just the Euclidean spaces Rn. In schemes, they at least include the free affine schemes. I don't know if those are all of the differential objects, but those are differential objects in the category of schemes. And in our example of differentiable infinity categories, the differential. See, I've already got something wrong here. I don't know if you can see I'm highlighting the word differentiable here. That should say differential. So, this was, again, another area of confusion is that in this infinity category, the objects are differentiable infinity categories. And now we're looking for differential objects in that category. And as you can imagine, this is not the best, not the best terminology, perhaps, but we borrowed it from Lurie in one sense and Cockett and Crotwell in the other sense. So we sort of stuck with it. But anyhow, what is the answer? The answer is that these are the stable infinity categories. So that's a nice sort of conclusion because it fits with the kind of intuition for Goodwille calculus. That there's a kind of intuition in Goodwille calculus that the sort of flat infinity categories or the tangent spaces should be stable. Should be that's the that I mean, this was already Goodwille's intuition that the analog of the tangent spaces should be stable categories, and so this putting the Goodwille tangent structure into a precise form allows us to make this a theorem that the differential objects really are precisely the stable infinity categories. Okay, so that was one sort of example of taking general theory of tangent structures and looking at what they correspond to in our example. There's another case I'd like to mention, which actually is sort of part of the motivation for this whole example, which was to think about sort of higher order objects, so here is a definition of an n-jet. So you have n-jets of smooth maps between smooth manifolds. You can say when two maps between smooth manifolds agree to order n. I think I've written out so here is what that means just in terms of ordinary manifolds. It means that two maps agree in local coordinates at a point up to degree n in their Taylor expansions. So that's a notion that you can abstract to any tangent infinity category. And then you can ask, what does that look like in your favorite tangent infinity category, for example, the Goodwille tangent structure. And so this really was the theorem that for us told us that what we were doing really does capture Goodwille calculus. And so in Goodwille calculus, you have these higher excisive approximations. So Goodwille defined a notion of n-excisive, which is a sort of polynomial of degree n, and an n-excisive approximation, which plays the role of the sort of nth term, or the nth truncation of the Taylor series. And so the theorem that we wanted was that these n-jets correspond to equivalences of these n-excisive approximations. And so for us, that theorem says that really all of Goodwille calculus, the whole kind of theory of Goodwille calculus, is encoded in this tangent structure. You can recover the notion of n-excisive approximation from our tangent structure, and therefore you can recover sort of the whole of the theory of Goodwille calculus. So this was really one of the main things we wanted to prove, and it, in my mind, this justifies, as I said, calling this the Goodwille tangent structure, because it really does capture Goodwille's calculus of functors. So there are other things. There are other concepts from the abstract theory of tangent structures that you might want to try to work out. Here is a list of a few papers that have been developing the theory of tangent structures. So there's differential bundles or vector bundles, connections and curvature, differential forms, affine spaces. So each of these is a notion you can develop in the abstract world of tangent categories. And so for me, the next step is to try to say, okay, well, what do these look like in the Goodwille tangent structure? What concepts do they sort of recover? How do they relate to the theory of Goodwille calculus that has already been worked out to a greater extent? So I haven't really made any progress with any of these. I've thought a little bit about connections and tried to understand, for example, what is the curvature on an infinity category, but that's still in very much the early stages. All right, so I've just about reached an 8 o'clock my time. I do have a few more slides here about infinity toposes, so I'm happy. I think I won't talk through these. If people have questions, I could try and explain a little bit about that extension or that kind of follow-up paper. But this was really the conclusion of the project with Christine and Matthew, to understand the Goodwille tangent structure as an example of a tangent infinity category. So I think I'll stop there. Thank you very much.
Okay, thanks very much for a nice talk. We have our usual sort of silent round of applause, so that was very nicely presented. So if anyone has any questions, you're welcome to go ahead and ask, or comments.
I mean, if nobody has questions, just in that case, I would like to ask what the last 3 slides say.
Okay, well, I can. So let me try to summarize these last 3 slides, and they are about infinity toposes and 2 tangent structures on the infinity category of infinity toposes. So you know, as I've written here, there are really sort of 2. So there's a category, an infinity category of infinity toposes, and then there's its opposite. A morphism of infinity toposes is really an adjunction, and you can take either the left or right adjoint, and so you get sort of 2 versions of the infinity category of infinity toposes, depending which of those you take. And so the main theorem then is that there are tangent structures on each of these. And very much I like to think of this as analogous to the 2 tangent structures on commutative rings. So commutative rings, again, you can sort of view as, algebraically as rings, or geometrically as affine schemes. And there are the 2 tangent structures I mentioned earlier, each give you sort of a tangent structure or notion of tangent bundle on a ring. And this is a very analogous situation. So there's a tangent structure on the kind of algebraic version of infinity toposes. And so that's number 1 here. And that is just a restriction of the Goodwille tangent structure that I described earlier. But then it turns out that that restriction has an adjoint, which gives a tangent structure on the opposite category, the one where you take the geometric morphisms. And so, so we're in the same situation as for rings, where you have these 2 dual tangent structures on an infinity category and its opposite. The first one, as I said, is just the restriction of the Goodwille structure. So I feel like I understand that one pretty well. But the second one, I feel like I don't understand at all well. You can do some calculations, which I've put on the last slide here. I've put just a little bit of what you can say about this geometric tangent structure, and in particular, how it, you can sort of work out what it does for so-called injective infinity toposes. But in general, I feel like I don't understand it very well. And so there are some sort of basic questions, which is just to work out the previous theory for this geometric tangent structure. What is a differential object? What are the n-jets? Even just what is the tangent bundle on something like sheaves on a space? So there are some sort of basic questions there that I would like to know, but it's having these sort of 2 dual tangent structures, it seems like an interesting setup.
Any more comments or questions?
Does this geometric tangent structure restrict on just one toposes?
I doubt it. Or at least it might restrict to something not very interesting. Would be my guess.
For this, yes.
I'm sorry?
You need infinity for this, yes.
I think so. I think so.
Any more comments or questions?
Yes. Mike, I would like to thank you for a beautiful talk. And in fact, that's good that you made it virtual in Brno, because our late colleague Ivan Kolář worked quite a lot with wire algebras in differential geometry. And when I wrote my paper, I consulted these things with him. And it's simply amazing how far this story goes.
Well, thank you for developing that theory to begin with, because this has been a really fun project for me to see this connection and to develop the, I studied Goodwille calculus for many years, and there was always this this intuition or the idea that it's analogous to tangent bundles on manifolds, but I never knew how to make that analogy precise. So it's really been fun to learn about this theory and actually see that it can be made precise. So thank you.
Okay. Well, if there are no further comments or questions, then let's thank Michael again for a lovely talk. And yes, so next week we'll have Mark Kamsma talking about something to do with model theory and category theory. We don't have a title yet, so we can stop recording for today.